No, saying pending, but it will record, I guess. Yeah, okay, good. All right, thank you. So, welcome everyone, and good morning. And let's start with today's lecture. So, last time we talked about some like basic introductory stuff about operating systems. So, today we'll discuss a little bit more detail about processes and what are processes. So, if you remember last time, I told a working definition of a process. Does anyone remember what it was? Anyone? Just unmute yourself and say. No? What is the process? Last time we discussed it. Okay, so this way, everyone is expecting somebody else to answer. Maybe you can type it in the chat. Nobody's typing into the chat also. So, okay, this way, I think this is not very good. Can everyone hear me?
Yes, sir, you're audible.
Okay, then please answer. What is the process?
The execution of a program.
Not execution of a program. So that would be called processing. But yeah, I mean, it's close. It's an executing program or a running program. Okay. So we'll see what is the difference between a program and a process in a short time. And what is a program basically? It's instructions, that is code. Okay, maybe I'm writing too thick. Some, let's say, static data. The data that is needed to like let's say some initialized variables, etc. Like when you write a program, you like define some variables and then okay, good. Now generally, so we talked about abstraction. So generally what happens is we want to run more than one program at a time. Okay. And these can be many, like browser, Teams, music, etc. Okay. And in fact, in a typical modern OS, hundreds of processes or programs are running at the same time. Okay. So how does this happen? So, but but we also know that there is only one or at max a few processors. Only one. Some lag. One or a few processors. Okay, there is some lag. I don't know. My computer is running slow, it seems. Okay, hopefully. Okay. And somehow now the problem is that now we want to supply the processors to each program, and basically we want to make it feel like there is an endless supply of CPUs. So give the illusion supply of CPUs, even though there is only one. Or at max, a few. Okay, good. So this is the problem that we want to solve. And what is the solution for this problem? It is virtualization of the CPU. Let's do it this way today. Nice. Okay. So what is the solution to this problem? This is going to be virtualization of the CPU. And last time I talked a bit about what is virtualization of the CPU, but today we'll see it in little more detail. So this is what it is going to be. And basically what it's going to be, run one process, then stop it in the middle. If you have any doubt or any question, just unmute yourself and ask, because as I said, I won't be able to see the Microsoft Teams screen since I'm screen sharing. Okay. Middle, then run another process and continue this. Okay, good. And this thing is called when this is done, it's called time sharing. I don't know why there's so much lag. I'm sorry about that. I am planning to get a new device, so hopefully soon we'll not have this problem. Okay, fully it works now. So this process is called time sharing. Okay, and time sharing of the CPU. And of course, like it comes at a cost, and its cost is going to be the performance, because whenever we do this, like each process gets less time, or program gets less time on CPU. So it will be slightly slower. Okay. But the hope is that we can do it fast enough such that we can keep the illusion of that the process is running all the time. Okay. So just like here we have time sharing, similarly, so time sharing of CPU, each process shares the CPU, right? And what is the like? So another thing that we'll see is memory sharing. Later lectures, where we'll see that how processes share the memory. Okay. Okay, good. Now, what does the operating system have to to achieve this virtualization? Okay. Virtualized CPU. So here there are two things that the OS can do, and I mean two types of thing that the OS has to do. So one is it has to make some low level decisions about how exactly it's going to virtualize the things, how exactly it's going to uh, stop one process and start another process and so on. So these low level things are called mechanisms. Okay, which are just some methods or protocols, like for example there is this method of context switching. So this is a low level thing that, I mean, this is more about the how. So low level things are concerned with the how, that how do you stop a process, how do you like load another process and so on. And then there is the high level things that the OS has to do, and these things are called policies, and they are concerned more with which, that which process to run, which process to stop, and when, and so on, right? So to run or stop, etc. Right? And the example can be some scheduling policy. Again, we'll see these things in detail. Okay. And like, so scheduling policy, some scheduling policy will be used by like the OS, and like what is a scheduling policy? So it will decide that which program to run when, and it might like take things into consideration. Things like let's say, historical info that earlier, if the process had run, then how much time it had taken, how much intensive it was, when was the last time the process was scheduled, and so on. Workload knowledge, how much the process is going to take, like, the CPU, how long, how intensive it is. And then some performance metrics of the CPU itself, that if we schedule the processes in this way, then how quickly the jobs can be finished, and so on. Okay. So these are the things. Again, we'll see them in detail when we talk about scheduling in detail. Okay. So this is like, these are the two kinds of things that the OS will have to do to run a program, basically, to create a process, right? All right. Now let's see it a little bit into detail, that uh, like what makes up a so process, or let's ask this question in a different way, that how is it different from a program? Again, we have seen it, like, in just a glimpse, that it is different from a program, that like a process is a running program, but let's see it in a little bit more detail, right? Okay, so the process has this thing called a machine state, which is what which constitutes of what a program can read or update while running. Or, okay, so here my writing is becoming worse because of the pen. So, or in other words, what parts of the machine are important for execution of the process? Okay, so now what this, like, so this is a broad description of a machine state, but what does machine state consists of, or what are the components? So one is going to be, of course, the memory, because a process can update and read memory. So basically, that is the memory that address, and it can address in both the forms, like read or write, and this is called address space of a process also. Okay. And then there are registers. like let's say the program counter, which points to the next instruction to be executed. So I'm sure you might have seen program counter earlier. If not, we'll see it like a little bit in more detail. So this is about next instruction to be executed. And something like stack pointer or frame pointer, again, like we'll see these when we do memory management in detail. And another component of machine state is going to be some input output information, whether like some keyboard is attached and whether we are typing something on the keyboard, or this crappy machine that I'm writing on and it's not working very well. So IO information. And so these are like roughly the components of a machine state, right? Now, when the OS wants to run a program, so it has to like maintain these things in some way, and it has to give the user also some ways to modify these things, or like basically to run a program, right? So an OS also provides these things, as I had told last time, called process APIs, application programmable interfaces. Okay. So process API is like, let's just discuss the like some very basic features which must be. So which are the features that must be included in any interface? Like what would you want a user to do? At least like, the minimum kind of functionality that you would want to provide. So what are the features that any OS must include? Okay, so we'll be discussing just those basic features that like any OS would have. So first one is definitely going to be creating a process, right? So there should be an API which creates a process. Because otherwise, I mean, how do you work? Like, how do you run any program? Create, okay? So as the name suggests, create new processes. And can someone tell an example of what kind of APIs are there to create new processes? How do you create new processes generally in any operating system, whatever system you are working on?
There's the fork system called
Sorry?
fork.
Fork. Say it again. Sorry. My volume was a little low.
Fork.
Fork. Yeah, but so basically fork is one way to create a process, but this is a more general thing that, okay, any OS, like for example, if you are in Windows, if you are in any operating system, basically you double click on a, like, an icon, and that will send the message that the OS will have to create a process. Or you type any command, not just fork, in a shell, and that will create a process, right? So type a command in shell. So, yeah, please unmute. Sorry, please mute yourself, whoever has not, because now I have increased the volumes and now I can hear some like disturbance. So, okay. So, type a command in shell or double click. Yeah, I'm used to writing the other click, so this click does not come very naturally to me. Okay, so type a command in shell or double click on an icon and so on. Okay, and these things create new processes which run a desired program. Right. Good. What is the other thing that any OS would need? It is to destroy a process. So usually processes exit on their own. But when not, when they don't, we might want to use this destroy to kill. Destroy to kill. That's like, sounds very violent. Okay. Then there is some functionality called wait, which is always there that, okay, wait for the process to finish. So I can still hear something. So if like, please mute yourself if you're not speaking. And then there is some miscellaneous control. Like, let's say, minus hard to draw. Like, let's say suspend or resume. And then status, like a user might want to get status of a process that, okay, whether it's running or not running or what happened to it and so on. So an OS also provides some way to get the status of the process. Okay. So this is just to get the status of the process. All right. So now these are the APIs that the OS provides. Now we'll see that what goes into creation of a process into a little more detail. Okay. So how is a process created?
Sir,
Yeah.
so all the processes use the same API for a given OS.
I mean, yes. So API is just a set of functionalities which are provided. So that depends on the user. So that's why they're called programmable interfaces. So now, like, there can be different ways of starting a program or a process. And one can be like double clicking, one can be like typing a command in the shell. And these are all provided by the OS to the user. Now it's up to the user which one he or she wants to use to, like, create the process. Does that answer the question?
Yes, sir.
Okay. So yeah, I was going to talk a little bit more detail about process creation. So I just said that, okay, the OS creates processes and it has to do, but what are the, like, how exactly are programs transformed into processes. Okay. Okay, so yeah, my machine has given up again. Okay, so or what does the OS have to do? Okay, this is okay to run a process. Okay, cool. So where do programs reside? So programs are on disk. So first thing that the OS will have to do is OS has to load okay, so if you don't understand something, please ask, because this is like very load the code, which is the instructions. Come on. Okay, let me run the syncing off. That will help. Okay, I can't turn off the syncing. Okay, all right. Load the code, which is the instructions. And the static data. Right? And into the address space of the process. So this code is generally, when there is a program, it is in executable form, right? So basically what happens is that suppose you have the disk, so here you have the disk and okay, very nice. And the program sits here. And what does the program have? It has some instructions or code and some static data. And here is suppose the CPU, and this is the memory. Okay. So what the CPU will have to do, or the OS will have to do, it has to bring this into here. So there is of course some connections between these all to this stuff. And when you'll bring it, There will be the code or the instructions, the static data, then you'll have the heap and the stack also. And shortly I'll tell what these things are. Okay. So basically the OS has to load these things. So earlier what used to happen is like, it was, so there can be two ways of loading this. One is called eager. So eager loading, that you bring all of the program at once. So you can fill in the details here. And now what is done is called lazy loading. And where only the parts are that are needed are loaded into memory. And again, we'll see this in more detail in like paging and swapping things. So this is later lectures. So basically we can divide the program into like these things called pages and just bring it one page by one and do it lazily. But this is the basically the first step. Okay. So let's write down the steps. So first is, I mean, not first, they can be performed like in any order. Not in any order, but still, it's not like in this order exactly. But copy the static data and code into memory. Okay. Then there is this thing called stack, as I've written here, right? So then the OS will have to allot some memory to the program stack. So can anyone tell what does the stack have? You might have seen in C, and you might have talked about the stack. So what does the stack contain? Anyone? What does stack of a program contain, or just stack?
It contains the local variables and the parameters that were passed to the function.
Exactly. So local variables, function parameters, and function parameters, and some return addresses maybe. Okay, and it also initializes the arguments for the main function. Main function of the program. Like argc, argv, okay, and then it also allocates some memory to the program's heap. So now what is in the heap? Anyone?
Global variables.
And what is the heap used for?
Essentially for data that we don't want to be bound to any function.
Exactly. Or not just that, the heap is where basically when a program asks for space, that's where the space is allocated. So that is like one of the that whenever we do malloc, the space is allocated from the heap. So that is the dynamically allocated data. So it's not just about local and global variables. Like major function of the heap is going to be to allocate data dynamically. Okay. So some memory allocation again. Yes. To programs heap. And as I said, heap is for dynamically allocated data. And how does the function request for some memory? How does the program request for some memory? What is the function?
Malloc.
Malloc. So malloc is for okay asking for it, asking for memory, and what is for freeing? It's just free.
Sir,
Yeah.
so could you please explain what does dynamic allocation mean?
Dynamic allocation means that, so for example, if suppose you are making a linked list or you are implementing, some hash table or some tree, and now you need more memory. So when the program is running, it is needing more memory. So it does not have a fixed amount of memory which it had from, beginning, but as it is running, it is like now asking for more and more memory. So now the OS has to allocate memory to the program, right? So that is why it's called dynamic allocation. That it's not static. It's not that only when the program started that at that time we gave the memory. It is done dynamically, and that is done in the heap.
Okay, sir. So when the stack is created, it's fixed with the like it's created with a fixed memory.
Yes, I mean anything when it's created with a fixed thing. But of course, even stack. Okay, I'm not sure like how many OSs can do that. But yeah, everything when it's created with a fixed memory. That okay, and when that memory is getting to be used or something, and then like the OS will have to allot more space to it. Even the heap, when initially it will be a fixed size, but now as and when the program will use malloc more and more times, then it will have to give it more and more space. Okay, does it answer the question?
Yes, sir. Thank you.
Okay, cool.
Excuse me, sir.
Yeah.
Sir, you told that means this local variables and all is contained in stacks, and if I am creating some linked list or let's say set, then it is allocated in heap, right?
Yeah.
So how actually OS differentiate between means which data to allocate there?
Okay, so I mean the program. So that's what I'm saying. That whenever the program asks for malloc, then it will save it in the heap, and the program will have something like written like global. Okay, so if it has something written global, then it will store it in the heap. If it is just some variable which is local to the program, then it will store in the stack. So the basically the description of the program will tell the OS, because when the instructions are running, so a program is executable. So the instructions, so whenever you write a C code, it will be put into assembly code and so on. So now the assembly code will tell that whether will depend upon whether the variable is going to be global or local, or whether like the process is asking for memory, and depending on the assembly code will be generated, and then the OS will can decide that whether it's going to be like a local variable or global variable or not. So like in short, the program's description will have these things.
Basically, you are saying even if I am creating linked list locally, then it will be stored in stack.
No, I'm saying it will be stored in the heap if you are using malloc to create the linked list. Depends on how you create the linked list, right?
Okay, sir.
Sir,
Yeah.
is there any reason we are using heap for allocating extra memory?
I mean, there can be different data structures, but okay. So, what do you think will be a better idea?
I mean, we can do it in the another. We can maintain another stack. We can do it in that one.
So these are some policies, and actually heap is like considered for better for these things, because there are some kind of operations which are easier to perform in a heap. And okay, so we'll discuss this. And so right now, I think we'll do it when we discuss memory, that why these data structures are better for allocation of memory.
Yes.
Any other question? Okay, good. So there is one more thing that the OS needs to do before like the program actually runs, and that is initializing some IO tasks. This is agonizing. Initializing IO tasks, like for example, every like in Unix, what happens is every process will have these three things called like some where. So what is the exact word for it? So these are called
File descriptors.
yes, file descriptors. Thank you. These are the file descriptors for input, output, and error. So that the program can easily deal with these things, or easily interact with. So basically, what these file descriptors have, they what the input devices are, whether something input is coming or not, or what is in the output, what is to go in the output, and so on. So these are the file descriptors for that, and the program can easily.
Sir, sir, but you have written below the input output.
Yes.
Sir, but you have written it's not clear. Input output, what is the third pointer?
Errors.
Error. Okay.
Yeah. And here it was Unix. Yeah. So Unix has these three kind of file descriptors. And finally, what does the OS do? So it copies the data, memory allocation to like stack, heap, initializing the arguments for main, initializing some IO tasks, and finally transfer the control to main. And we'll about this IO we'll see more in the when we do persistence module. And yeah, I mean, my writing is bad, but it's not as bad as it's making it look like. Transfer control to main. And how exactly, we'll see in next lecture. Okay. So this is the this is all that, like, this is mostly all what like OS has to do to basically initiate a program, and when it transfers control to main, then the program starts executing. Okay. So okay, good. So now we'll also learn about these things called process states. So, I mean, let's look at a simplified view where there are 3 states. One is running, which is self-descriptive. So the process is running, basically executing. It has the control. Second is ready. The process is ready to run. But for some reason OS has decided not to run it. Run it right now. Okay. So what can be the reasons that OS is executing something else? Okay. And finally, it's called blocked. So something has blocked the way of the process. What does that mean? That process is waiting for something to happen. Process has performed some operation. Performed which requires some events to happen. Okay. And then only the process can start execution. So generally this is in form of like some IO request. So process makes some IO request, and now it has to wait for like the input or output to be performed before it. So block till request is completed. Okay. So let's see it by an example, like, a short example. So basically, actually, so these are the 3 states. Let's say running. So this diagram you can find in the chapter also. Ready and blocked. So from running to blocked, it can come by some IO request. Request initiation. And from block to ready when IO request completes. And from running to ready if descheduled. And from ready to running if a process has been scheduled. Okay. So we say a process to be scheduled if it has gone from ready to running, and if it has gone from running to ready, then we call it descheduled. Okay. So, like for example, let's say there were two processes. So there is this example in the book. So let's just go through that. So let's say time, process 1, process 2, and let's write here what is actually happening. So let's say initially process 1 was running and process 2 was ready. It was loaded into memory. All the things were initialized, but it is still not on the processor and running. Let's say time 2 also this happens. Let's say at time 3, process 1 makes, it is still running, but it makes, let's say, some IO request. Okay. So now it has to wait. So what the OS will do, it will block this process, and now this will start running. Okay. Suppose this is still running. Then at the next instance, suppose, and now suppose the IO request gets completed. Now what will happen? Now this is ready, but maybe not yet running because this is still running, and it runs for one more step, and now process 2 finishes. And then now this will be scheduled. Process 1 is scheduled. Again, come on. And this is now exited, finishes and exits. And 10, the final step. This is still running. This has finished, and now process 1 also finishes and exits. Okay, so this is one example, which is there in the book also, where you can see that, how these controls are transferred. So now you see that even after the IO request completed, here, the process kept program 2 running. right? So is that good or not? Depends on the context. So this is a decision OS will have to take. And this comes under like scheduling policy. And we'll see this also in detail later. So what the OS might have done also was like, as soon as the IO request completed, it will put process one there and start running it and so on. Okay. So this is like what, states of the process look like. But this is like some kind of simplified view of the states of the process, because generally the operating system has like more states in which a process can be, and then it shifts between those. And also, if suppose there was no input output there, there was no input output request there, then like, process one will be running, and then process two will be ready, and then process one will exit, or maybe if runs for too long, then process two can, just run in between and so on. So there will be no blocked state if there is no input output state in that case. Okay. So that is about process states. And now we'll talk a bit about the data structure that the OS uses for processes. Okay. So first thing is like, the OS will have to keep a list of all the processes, right? And ready, blocked, running, all kind of processes, right? And also some data that, okay, whether they are running or, what is their status. So first is the list of processes, and then whether which one is running, blocked, etc. Okay. In addition, for block processes, they also have to see, like, the OS also has to see that whatever the input output request the block process had made, what is happening to them when they complete, because when they complete, then the OS has to transfer the control back to the block process. Come on. So the OS has to track the IO requests, and so that it can transfer the control back. Back to the process when it finishes. Your request is complete. Okay, good. Now, what what will be there in a process, so what is the information that the OS keeps about a process? So of course it keeps a lot of information, and we are not going to deal with like the whole data structure of a process, but what are the typical things? Okay. Okay. So one thing that like it will store, okay, we'll come to that. So one thing that it has is the register context. Basically, like contents of all the registers when process ran last time, or when the process was stopped last. So why is this needed? This is needed for context switch, that okay, now you want to stop one process and shift to another process and so on. So you have all this data which can be directly loaded into the registers, and then the process can start from there. Okay. Stopped. Okay, good. And it needs process state, of course. Like just like I said, like running, blocked, maybe some other state that the OS might decide. So actually, there are more states in modern OSs. Stack pointer. Okay, no, before that, start of the process memory. That where does the memory block start for the process? And then size of the process memory.
Sir,
Yes.
so when a process gets blocked because it has sent some IO request,
Mhm.
will the content it had in its registers it might get wiped off, right? For other processes.
So from the register, and that's when we'll store it in this register context.
Yes, sir. So that's the use, right?
Yes, yes,
Okay.
exactly.
Thank you, sir.
Because now we want to schedule some other process there. So then that process will have its own register contents. It will have its own program counter. It will have its own stack pointer and so on. So we don't want to lose the data about the process that we are descheduling for now, or we are blocking for now. So we'll copy that into the register context. So yeah, that's the use. Thanks. And this will be like, this is used for this thing called context switching that we'll see again. Okay, and then for example, like pointer to bottom of stack. or let's say like there is this thing called PID, process ID. There is whether there is any parent process. And like open files, that also it is there, whether the process has opened any files, what is the current directory. So yeah, I mean some info about how to handle interrupts or traps. That what happens or where to go when, like, when some error happens. So these are, like, typically things, but of course there will be other things, because generally it is there are much more complicated things which are happening when a process is running. But like these are typically the things that like we can understand for now, and that we'll see in later lectures and so on. So this is like um, mostly it for today's lecture. And so these are, yeah, so this is the information that the OS keeps. And then in the next lecture, what we'll see is how the, like, the initialization and other things, how the control is transferred to the process in reality. Okay. So just to recap, let's go up. So what did we see? First, we saw the, like, difference between process and program, and what does it mean to virtualize the CPU, and how does the OS do that. And then we talked about, okay, what is actually the difference between program and process, what are the details. Then we saw what are the kind of functionalities that the OS provides for managing a process. Then we saw how a process is created, what are the steps that the OS has to do, and then process states, and finally, what is the data structure for the process. So, any questions about these things? Okay, so I'll stop sharing for now. So, yeah. So, your TAs might be giving you some. Okay, let me also just quickly take attendance. And I talk to the TAs. They will be giving you some like working assignments. Please do them. They'll be very important in, like, brushing up your things and so on. And what else I was going to say? Yeah, and they would fix some time with you for there will be a 2-hour slot in a week when you can interact with them. You can ask questions. If you have any doubts about the course or anything, they have set up a Piazza. You can write your questions there. Your classmates or the TAs or me, somebody will answer your queries. And what else? Yeah, I don't think there's anything else. If there is any question, please ask. Okay, no questions? Cool then. Thank you all for coming to the class, and I'll see you guys on Thursday. Yeah. Okay, cool. Thanks.
attendance. You said